The conference room at Rand Corporation in Santa Monica fell silent when Amrom Katz finished his presentation. It was 1960, and the 42-year-old physicist had just proposed something the Pentagon brass considered absurd: using satellites to verify Soviet compliance with future arms control treaties. An Air Force colonel leaned back in his chair and asked the question everyone was thinking. How exactly do you expect a camera orbiting 100 miles up to tell us whether the Russians are cheating? Katz had spent the previous 18 months running calculations that kept him awake until 3 a.m. His office at Rand was cluttered with film samples, optical diagrams, and resolution charts covered in his meticulous handwriting. The math was unforgiving but clear. A satellite-mounted camera with a 24-inch aperture lens operating at an orbital altitude of 160 kilometers could theoretically achieve ground resolution of 1.5 meters. That meant distinguishing between a bomber and a fighter jet, between a missile silo under construction and a grain elevator, between compliance and violation. The problem wasn't just technical skepticism. The entire arms control establishment operated on a fundamental assumption. Verification required inspectors on the ground, physically counting warheads and measuring missiles. When President Eisenhower's advisors discussed potential treaties limiting strategic bombers, they envisioned teams of American officials touring Soviet air bases with clipboards and tape measures. The Kremlin would never allow it, which meant treaties were impossible, which meant the arms race would continue until someone miscalculated and civilization ended. Katz saw a different path. If reconnaissance satellites could photograph Soviet military facilities with sufficient detail, both superpowers could verify compliance without ever setting foot on each other's soil. No inspectors, no sovereignty violations, no excuses. Just objective evidence collected from orbit, analyzed by experts, and presented to negotiators who could then proceed with confidence instead of paranoia. The Rand presentation ended badly. Military intelligence officers argued that satellite imagery would never replace human intelligence networks. State Department representatives worried that relying on technology would eliminate negotiating leverage. Even some of Katz's colleagues at Rand thought he was overselling capabilities that didn't yet exist. The U-2 spy plane program had proven that aerial reconnaissance could capture valuable intelligence, but satellites were unproven. The first Corona reconnaissance satellite wouldn't successfully return film for another 7 months. Katz walked out of that conference room knowing he'd failed to convince the people who mattered. But he also knew something they didn't. The technology was already advancing faster than the bureaucracy could comprehend. Eastman Kodak was developing new film emulsions with finer grain structure. Optical engineers were designing lens systems that could compensate for atmospheric distortion. And most importantly, the laws of physics didn't care about institutional resistance. He returned to his office and continued working on what would become a 300-page classified study titled Observation Satellites and Arms Control. The document meticulously detailed how orbital platforms could verify limits on bomber deployments, missile installations, and nuclear test sites. It included specific technical requirements, minimum resolution thresholds, optimal orbital parameters, and the number of satellites needed for continuous coverage. Katz wasn't proposing a vague concept. He was engineering the future of strategic stability, one calculation at a time. Amrom Katz never planned to become the architect of satellite verification. He'd spent the 1940s at the University of California studying cosmic rays, analyzing particle tracks in cloud chambers, developing techniques to extract meaningful data from photographic evidence of invisible phenomena. His dissertation involved building detection equipment sensitive enough to capture events lasting microseconds. He learned to trust what cameras could reveal when human eyes couldn't see anything at all. The transition from academic physics to intelligence analysis happened almost by accident. In 1948, the Air Force needed someone who understood both photography and physics to evaluate aerial reconnaissance technology. Katz took a temporary consulting position at Wright-Patterson Air Force Base in Ohio, expecting to return to academia within a year. Instead, he discovered a problem that consumed the next 2 decades of his life: how to extract strategic intelligence from photographs taken at extreme distances. His early work focused on interpreting images from conventional aircraft. The challenge wasn't just resolution, it was understanding what you were looking at. A photograph showing rectangular structures near a Soviet city could be apartment buildings, warehouses, or bomber assembly facilities. Katz developed analytical techniques that combined image quality assessment with contextual intelligence. He measured shadows to determine building heights, calculated dimensions from known reference objects, and identified facilities by their spatial relationships to roads and rail lines. By 1956, when the U-2 spy plane began operational flights, Katz had moved to Rand Corporation and established himself as the leading expert on photographic intelligence analysis. He spent hours examining U-2 imagery with stereoscopic viewers, identifying Soviet bomber bases by the distinctive patterns of hardened aircraft shelters. The resolution was extraordinary for its time. U-2 cameras operating at 70,000 feet could distinguish objects 60 centimeters across. You could count aircraft on a runway. You could measure missile components in a factory courtyard. But aircraft had limitations that Katz understood better than anyone. They required overflight permission, which the Soviets would never grant, meaning U-2 missions violated Soviet airspace and risked international incidents. They were vulnerable to improving air defense systems. Eventually, one would be shot down, and the diplomatic consequences would be severe. And most critically, they couldn't provide the continuous, reliable coverage that arms control verification would demand. Katz began thinking about satellites in 1957, immediately after Sputnik demonstrated that orbital platforms were technically feasible. His background in particle physics gave him an intuitive understanding of the challenges involved. Cosmic ray detectors had taught him how to design instruments that functioned reliably in extreme environments. Photographic analysis had shown him exactly what resolution capabilities would be needed for strategic verification. The question wasn't whether satellites could work. It was how quickly they could be made good enough. He filled notebooks with orbital mechanics calculations, determining optimal altitudes that balanced resolution against atmospheric drag. He corresponded with optical engineers about lens designs that could maintain focus across 160 kilometers of atmosphere. He studied film chemistry, trying to identify emulsions with sufficient sensitivity for the short exposure times that orbital velocity demanded. Every technical obstacle had a potential solution. What Katz couldn't solve with calculations was institutional inertia, the deeply embedded belief that verification required physical presence, not remote observation. By 1960, when he presented his findings to skeptical Pentagon officials, Katz had already moved beyond whether satellite verification was possible. He was working on the precise technical specifications that would make it inevitable. On May 1, 1960, Soviet SA-2 missiles shot down Gary Power's U-2 at 70,500 feet over Sverdlovsk, creating an international crisis that paradoxically strengthened Amrom Katz's argument for satellite verification. The diplomatic disaster proved exactly what Katz had been saying. Aircraft surveillance was politically unsustainable. But before Power's capture ended the U-2 program over Soviet territory, those missions had generated something unprecedented: photographic proof that overhead reconnaissance could verify arms control agreements. Katz spent weeks analyzing U-2 imagery that CIA photo interpreters had collected during 4 years of overflights. The evidence was irrefutable. Camera systems aboard Power's aircraft and earlier missions had photographed 29 Soviet ICBM complexes, identifying them by the distinctive radial pattern of access roads leading to launch facilities. At the Turatam test range, U-2 cameras captured images showing individual R-7 missiles on their launch pads. You could measure the missile's diameter at 10.3 meters and estimate its length at roughly 34 meters. The resolution was sufficient to distinguish between operational missiles and test articles. More importantly for Katz's verification thesis, the imagery revealed deployment rates. By comparing photographs taken 6 months apart, analysts could count how many new ICBM silos had been constructed. They could track progress on bomber production by monitoring assembly facilities at Kuibyshev and Kazan. When the Air Force estimated Soviet strategic bomber strength at 1,500 aircraft based on theoretical production capacity, U-2 photographs showed the actual number was closer to 190. That discrepancy mattered enormously for arms control negotiations. You couldn't verify limits on weapons that didn't exist. Katz documented these findings in classified briefings that circulated through the intelligence community. His analysis included specific examples of what verification photography required. To confirm that a suspected ICBM site was actually a missile complex, you needed resolution sufficient to identify launch control buildings, propellant storage tanks, and the concrete flame deflectors beneath launch pads. U-2 cameras achieved 60-centimeter resolution, barely adequate, but workable. Satellites would need to match or exceed that threshold. The shoot-down actually helped Katz's case in an unexpected way. President Eisenhower's advisors were desperate for alternatives to aircraft overflights that wouldn't trigger World War III every time they violated Soviet airspace. Satellites operated in space, which wasn't technically anyone's territory. The Soviets might complain, but they couldn't shoot down a satellite at 160 kilometers altitude with 1960 technology, and international law regarding orbital sovereignty remained conveniently undefined. Katz pushed his advantage. He prepared technical assessments showing the satellite cameras, using the same optical principles as U-2 systems, could achieve comparable resolution from orbit. The key was aperture size and film quality. A satellite-mounted camera with a 60-centimeter primary mirror, using fine-grained film and precise attitude control, could theoretically photograph Soviet facilities with the same clarity that U-2s had demonstrated. The technology wasn't science fiction, it was engineering. By late 1960, Katz's verification concept had influential supporters. The CIA's Corona program was attempting to develop exactly the kind of satellite reconnaissance system Katz described, though initial test flights had failed spectacularly. But the U-2 imagery provided proof of principle. Overhead reconnaissance could distinguish between ICBMs and telephone poles, between bomber bases and civilian airports, between compliance and cheating. The question was no longer whether satellites could verify arms control treaties. The question was how quickly they could be made operational, because without verification technology, the alternative was endless weapons proliferation driven by mutual suspicion and worst-case assumptions. The first Corona satellite to successfully return film to Earth landed in the Pacific Ocean on August 18, 1960, after completing 17 orbits. Recovery crews fished the capsule from the water and rushed it to Eastman Kodak facilities, where technicians developed 3,000 feet of film containing more photographic coverage of the Soviet Union than all previous U-2 missions combined. Amrom Katz was among the first analysts to examine the imagery. What he saw convinced him that satellite verification wasn't just theoretically possible, it was already working. The Corona photographs revealed Soviet military facilities with startling clarity. Even with first-generation optics achieving only 7.6-meter resolution, analysts could identify bomber bases, shipyards, missile test facilities, and nuclear weapons complexes. Katz focused on specific verification scenarios. Could you count strategic bombers at an airbase? Yes. The distinctive swept-wing profiles of Tupolev Tu-95 Bears were clearly distinguishable from transport aircraft. Could you monitor ICBM silo construction? Absolutely. Excavation work created signatures visible from orbit, and concrete launch facility construction progressed through identifiable stages. The technology improved rapidly. By 1963, Corona satellites designated KH-4A carried dual panoramic cameras achieving 1.8-meter resolution. Katz could identify individual vehicles and motor pools, distinguish between different missile types on rail cars, and monitor construction progress at nuclear facilities by comparing imagery taken weeks apart. The film return system worked elegantly. Satellites exposed film for several days, then ejected re-entry capsules that parachuted into recovery zones where specially equipped C-119 aircraft snagged them mid-air with trapeze-like retrieval systems. But Katz understood that film-returned satellites had limitations for treaty verification. The fundamental problem was latency. Exposed film remained in orbit until the capsule was ejected, then required several hours for recovery and processing before analysts could examine it. If you photographed a suspected treaty violation on Monday, you might not have confirmed evidence until Thursday. For ongoing arms control monitoring, that delay was acceptable. For crisis verification during confrontations like the Cuban Missile Crisis in October 1962, when Kennedy needed immediate confirmation of Soviet missile deployments, it was dangerously slow. The solution was already under development. Katz had been briefing intelligence officials on real-time imaging satellites since 1961, arguing that digital transmission systems could eliminate film return delays entirely. Instead of exposing film and physically returning it to Earth, satellites could convert optical images to electronic signals and transmit them to ground stations. Analysts could examine imagery within hours instead of days. The technical challenges were substantial. Electronic imaging sensors in the early 1960s had nowhere near the resolution of fine-grained photographic film. Transmitting high-resolution imagery required enormous bandwidth, more than existing satellite communication systems could handle. And digital image processing technology was primitive. Katz spent countless hours working with engineers at iTech Corporation and PerkinElmer, analyzing trade-offs between resolution, transmission bandwidth, and sensor sensitivity. By 1965, Corona satellites had photographed every significant Soviet military facility multiple times, creating a comprehensive baseline for verification purposes. Katz used this archive to demonstrate how satellite monitoring could detect treaty violations. If an agreement limited ICBM deployments to 1,000 launchers, satellites could count silos and mobile launchers with sufficient accuracy to detect illegal additions. If a treaty banned certain bomber types, overhead imagery could identify prohibited aircraft at air bases. The verification wasn't perfect. Cloud cover could obscure facilities, and camouflage could complicate identification. But it was vastly better than guessing. What made Corona truly revolutionary for arms control wasn't just the intelligence it collected. It was the transparency it created. Both superpowers knew they were being photographed from orbit. Neither could secretly build up forces without detection. That mutual awareness made negotiated limits enforceable, transforming arms control from aspirational rhetoric into verifiable reality. The KH-11 satellite that launched from Vandenberg Air Force Base on December 19, 1976, represented everything Amrom Katz had been advocating for 16 years. Designated Kennan, it was the first American reconnaissance satellite to transmit digital images in near real time, eliminating the film return delays that had plagued treaty verification. More importantly, its imaging system achieved 0.15-meter resolution, sufficient to read vehicle license plates from orbit. The era of "maybe we can see it" verification was over. The era of "we can prove it beyond doubt" had arrived. Katz had moved to the CIA's Office of Scientific Intelligence by then, specifically to work on satellite verification systems. He'd spent years arguing that arms control treaties required sensors capable of detecting violations at tactically relevant timescales, not days or weeks later when diplomatic responses would be meaningless. The KH-11's electro-optical imaging system solved that problem. Instead of exposing film, The satellite used a digital sensor similar to television cameras, but vastly more sophisticated. It scanned Soviet facilities continuously, transmitting encrypted data streams to ground stations, where analysts examined imagery within 3 to 6 hours of acquisition. The resolution capabilities transformed verification from statistical sampling to comprehensive monitoring. At 0.15 meters, KH-11 cameras could distinguish between different missile types on launch pads. They could identify individual warhead shapes on re-entry vehicles, allowing analysts to verify MyRV deployments, multiple independently targetable re-entry vehicles that arms control negotiators were desperately trying to limit. You could see maintenance hatches on submarine hulls, count missile tubes, and verify that Soviet ballistic missile submarines complied with SALT limitations. Katz focused particularly on mobile missile verification, which had been impossible with earlier satellite systems. The Soviets were developing SS-20 intermediate-range missiles mounted on mobile launchers that could relocate between surveillance passes. KH-11's rapid revisit capability, the satellite could photograph the same target multiple times per day, meant analysts could track mobile launchers as they moved, maintaining continuous surveillance that prevented treaty circumvention through mobility. The technical specifications were extraordinary. The KH-11's primary mirror measured 2.34 meters in diameter, essentially a Hubble Space Telescope pointed at Earth instead of the stars. Its orbital altitude varied between 250 and 500 kilometers, optimized to balance resolution against atmospheric drag. The satellite weighed 13,600 kilograms and carried enough propellant for orbital adjustments that extended its operational life to approximately 3 years. Each KH-11 cost roughly $400 million in 1976 dollars. But that expense bought verification capabilities that made billion-dollar treaty violations detectable. Katz understood that resolution alone wasn't sufficient for treaty verification. The KH-11 incorporated multispectral imaging capabilities, capturing data across infrared and visible light wavelengths. Infrared sensors could detect thermal signatures from missile launches, nuclear reactors, and engine tests that were invisible in normal photography. Multispectral analysis could penetrate camouflage by identifying spectral differences between natural vegetation and camouflage netting, revealing concealed facilities that would otherwise remain hidden. The intelligence community remained skeptical about relying exclusively on technical collection for verification. Traditional human intelligence officers argued that satellites couldn't detect treaty violations hidden inside buildings or underground. Katz countered with evidence. KH-11 imagery showing ventilation systems, electrical infrastructure, and construction patterns that revealed underground facilities. You couldn't photograph missiles in a sealed bunker, but you could identify bunker construction, monitor access roads, and detect support facilities that indicated prohibited activities. By 1977, KH-11 satellites were providing verification imagery for SALT II negotiations, photographing Soviet ICBM fields and bomber bases with unprecedented clarity. Katz's verification architecture was operational. Negotiators could propose specific numerical limits on strategic weapons, knowing that violations would be detected, photographed, and documented with evidence that would withstand technical scrutiny. Trust wasn't required. Transparency enforced compliance. The moment Amrom Katz had been working toward arrived on May 26, 1972, in the Kremlin's St. Vladimir Hall. President Richard Nixon and Soviet General Secretary Leonid Brezhnev signed the Strategic Arms Limitation Treaty, SALT-Y, placing the first numerical limits on strategic nuclear weapons in history. The treaty restricted anti-ballistic missile systems to 200 launchers per side and froze ICBM deployments at existing levels. More significantly, Article 5 of the treaty explicitly prohibited interference with national technical means of verification, diplomatic language that meant reconnaissance satellites were now legally protected under international treaty law. Katz watched from CIA headquarters in Langley as the signing ceremony proceeded. He'd spent the previous 18 months briefing American negotiators on exactly what satellite surveillance could verify and what it couldn't. The treaty's specific numbers: 1,618 ICBM launchers for the Soviets, 1,054 for the United States, reflected verification capabilities, not abstract strategic theory. Those were the quantities that satellites could count with confidence. The verification provisions represented a fundamental shift in arms control philosophy. Previous disarmament proposals had collapsed because neither superpower would allow foreign inspectors on their territory to verify compliance. SALT. I solved that problem by making verification technological instead of physical. Corona and Koach 8 satellites had already photographed every Soviet ICBM complex, creating baseline inventories against which future deployments could be measured. Both sides understood they were being watched from orbit, and both sides accepted that overhead reconnaissance was the price of enforceable arms limitation. What made the treaty work, technically, was specificity. SALT. I didn't vaguely limit strategic weapons, but defined precisely what qualified as an ICBM silo, how to count ballistic missile submarines, and what constituted a heavy bomber. These definitions matched what satellite sensors could identify and distinguish. A silo under construction showed distinctive signatures: excavation patterns, concrete reinforcement, missile erector equipment, and control facilities. Katz had cataloged these indicators meticulously, ensuring that treaty language aligned with observable physical characteristics. The Soviets had their own reconnaissance satellites providing equivalent verification coverage of American facilities. This mutual transparency was crucial. Neither side could claim the other was cheating without presenting evidence that would reveal their own intelligence capabilities. The result was verification based on shared technical reality rather than political accusations. When questions arose about specific facilities, both sides knew exactly what the satellites had photographed, which created powerful incentives for honest compliance. The treaty included provisions for photo interpreters to brief negotiators on verification findings without compromising satellite capabilities. Katz helped develop sanitized briefing materials that showed what could be verified: ICBM silo counts, submarine deployments, bomber inventories, without revealing resolution capabilities or sensor specifications. American negotiators could tell Soviet counterparts, "We can verify this limit with confidence," knowing KH-8 imagery provided the necessary evidence. Critics argued SALT. I was inadequate because it didn't reduce nuclear arsenals, only limited their growth. Katz had a different perspective. The treaty established verification as achievable, transforming arms control from aspiration to mechanism. Before SALT-I, strategic limitations were impossible because verification was impossible. After SALT-I, verification was proven, which meant deeper reductions became negotiable. You couldn't disarm what you couldn't count, and satellites had made counting reliable. The treaty's real significance wasn't the specific weapon limits it imposed. Those would be superseded by SALT-II and later START agreements. The significance was establishing that technical verification worked. Nixon and Brezhnev signed SALT-I because both knew their strategic forces were being monitored continuously by satellites neither could destroy or evade. That knowledge created the foundation for every subsequent arms control treaty. Katz's vision from 1960 that satellite reconnaissance could enable verifiable limitations on nuclear weapons had become the operational basis for superpower strategic stability. Cloud cover over Soviet ICBM fields had always been Amrom Katz's nightmare verification scenario. Optical satellites, whether film-returned Coronas or digital KH-11s, couldn't photograph what they couldn't see. The Soviet Union's northern ICBM complexes experienced cloud cover 60 to 70% of the time. During crucial treaty compliance periods, weeks could pass without clear imagery of suspected deployment areas. A determined cheater could exploit these gaps, constructing prohibited facilities during cloudy periods and camouflaging them before the next clear sky satellite pass. Katz needed verification systems that worked regardless of weather, darkness, or deliberate concealment. The solution came from synthetic aperture radar, SIR technology, that used microwave pulses instead of optical imaging. Radio waves penetrated clouds, operated equally well day or night, and revealed structural details that optical systems missed. The physics was elegant. A satellite-mounted radar transmitted microwave pulses toward the ground and measured reflected signals. By processing these reflections with sophisticated algorithms, the system constructed images showing surface features, buildings, and vehicles with resolution comparable to optical photography. Development of orbital SAR systems consumed most of the 1970s. Katz worked closely with Hughes aircraft engineers who were designing radar imaging satellites designated LaCrosse. The technical challenges were formidable. Achieving useful resolution required enormous antenna arrays. The LaCrosse satellite carried a 15-meter deployable antenna that unfolded in orbit like a mechanical flower. The radar system consumed so much electrical power that the satellite needed solar panels generating 11 kilowatts, far exceeding earlier reconnaissance satellites. But the capabilities justified the complexity. LaCrosse achieved resolution between 0.3 and 1 meter, depending on imaging mode, sufficient to identify individual vehicles and distinguish between different types of military equipment. More importantly, SIR imagery revealed characteristics invisible to optical sensors. Metal structures produced distinctive radar signatures. Underground facilities could be detected by subsurface disturbances that altered surface drainage patterns. Camouflage netting designed to mimic natural vegetation and visible light had completely different radar reflection properties than actual trees. Katz focused particularly on mobile missile verification. Soviet SS-24 and SS-25 ICBMs deployed on rail cars and truck launchers specifically to evade satellite surveillance. These systems moved continuously, operating on the assumption that reconnaissance satellites couldn't track mobile targets. Synthetic aperture radar changed that equation. SAR satellites could image entire deployment areas regardless of weather, detecting mobile launchers by their distinctive radar cross-sections. A missile transporter erector vehicle showed a characteristic signature that couldn't be confused with civilian trucks or military equipment. The first LaCrosse satellite launched from Space Shuttle Atlantis on December 2, 1988. Within weeks, it was providing all-weather coverage of Soviet strategic facilities. Katz examined early SAR imagery showing ICBM fields in Siberia, photographed through complete cloud cover. The radar had penetrated weather that would have blocked optical satellites for days, revealing silo construction and launcher deployments with sufficient clarity for treaty verification. Combining optical and radar surveillance created comprehensive monitoring that closed verification loopholes. KH-11 satellites provided high-resolution imagery during clear weather. LaCrosse radar satellites covered the same facilities during cloudy conditions. Between them, they maintained continuous surveillance that prevented treaty violations from going undetected. A Soviet attempt to build prohibited ICBM silos would be photographed by optical satellites if skies were clear, and imaged by radar satellites if clouds obscured the site. There was no longer a window for undetected cheating. The technology enabled increasingly stringent verification requirements in START war negotiations during the late 1980s. American negotiators could propose limits on mobile ICBMs because SAR satellites could verify compliance. They could require specific deployment patterns because all-weather imaging detected violations regardless of meteorological conditions. Katz's verification architecture, combining optical, infrared, and radar sensors, had eliminated the environmental variables that could have undermined treaty enforcement. The technical specifications that Amrom Katz meticulously cataloged throughout the 1980s weren't abstract engineering details. They were the foundation of strategic stability. Every number mattered. Every capability directly enabled specific treaty provisions. When American and Soviet negotiators sat down for SALT II discussions in 1977, and later START negotiations beginning in 1982, The verification requirements they debated corresponded precisely to what reconnaissance satellites could detect, measure, and confirm. Resolution thresholds determined what could be verified. The 0.1-meter resolution achieved by advanced KH-11 variants meant analysts could distinguish between SS-18 and SS-19 ICBMs based on visible differences in their dimensions. The SS-18 measured 3 meters in diameter, while the SS-19 was 2.5 meters. This mattered enormously because SALT II limited the number of heavy ICBMs, defined as missiles with throw weight exceeding 5,500 kilograms. The SS-18 qualified as heavy, the SS-19 didn't. Satellites needed sufficient resolution to tell them apart, or the heavy missile limits would be unverifiable. MIRV verification required even finer discrimination. Multiple independently targetable reentry vehicles, MIRVs, allowed a single missile to carry multiple warheads aimed at different targets. Start. I limited the number of warheads per missile type. 10 for SS-18s, 6 for SS-19s, 3 for SS-25s. Katz's challenge was determining whether satellite imagery could count warheads on a deployed missile. The answer was conditional. During missile loading operations at production facilities, KH-11 cameras could photograph individual re-entry vehicles being installed on post-boost vehicles. Once missiles were sealed in silos, direct warhead counting became impossible, but imaging satellites could verify missile types and compare them against declared MIRV loadings. Multispectral imaging capabilities expanded verification beyond simple photography. Infrared sensors operating in the 3 to 5 micron wavelength range detected thermal signatures from missile fueling operations, submarine reactor compartments, and bomber engine tests. This enabled verification of treaty provisions restricting flight testing and deployment readiness. When the Soviets conducted an SS-25 test launch from Plesetsk Cosmodrome, infrared satellites detected the missile's exhaust plume within seconds, recording burn time and trajectory data that verified compliance with range limitations. Revisit rates, how frequently satellites could rephotograph the same location, determined the temporal resolution of verification. Advanced KH-11 satellites in sun-synchronous orbits achieved 12-hour revisit cycles over Soviet ICBM fields. This meant suspected violations could be confirmed within half a day, rather than waiting weeks for the next satellite pass. For mobile missile verification, rapid revisit was essential. SS-24 rail mobile missiles could travel 1,000 kilometers between surveillance passes unless satellites checked deployment areas twice daily. The numbers that emerged from these technical capabilities shaped treaty provisions directly. START I limited each side to 1,600 strategic nuclear delivery vehicles and 6,000 accountable warheads. These weren't arbitrary figures. They represented quantities that satellite surveillance could verify with acceptable confidence levels. Katz had calculated error margins for every verification scenario. ICBM silo counts had less than 1% uncertainty. Submarine-launched ballistic missile tubes could be verified within 5%. Heavy bomber inventory showed 3% error rates due to storage facilities that occasionally obscured aircraft. The verification protocols included specific technical provisions reflecting satellite capabilities. Treaty parties agreed to use functionally related observable differences, FRODs, to distinguish between missile types. A FROD was any physical characteristic detectable by national technical means. The SS-24's three-stage configuration versus the SS-25's single stage was a FROD. The different lengths of Trident I and Trident II submarine-launched missiles were FRODs. These observable differences allowed satellites to verify complex treaty provisions without requiring on-site inspections. By 1991, when START I was signed, verification technology had advanced to where negotiators could propose 50% reductions in strategic arsenals, with confidence that violations would be detected. Amrom Katz retired from the CIA in 1989, ending a 40-year career that transformed arms control from diplomatic aspiration into technical reality. He'd spent 4 decades proving that verification didn't require trust. It required telescopes, radar, infrared sensors, and analysts who understood what they were looking at. The architecture he built enabled treaties that removed over 12,000 nuclear warheads from operational deployment and saved both superpowers an estimated $30 billion in unnecessary weapons procurement costs during the 1990s alone. The legacy wasn't just technological. Katz established verification as a discipline, training generations of photo interpreters who could distinguish treaty-compliant facilities from prohibited ones. He created analytical methodologies that combined imaging intelligence with contextual understanding. You didn't just photograph a building, you analyzed its purpose from access roads, power infrastructure, waste handling facilities, and operational patterns. These techniques remained classified for decades, but became standard practice for monitoring not just Soviet compliance, but later Russian, Chinese, North Korean, and Iranian strategic programs. His fundamental insight, that mutual transparency reduces conflict risk more effectively than secrecy, became the operational foundation for every nuclear arms treaty negotiated after Salt Tuong. The Intermediate Range Nuclear Forces Treaty that eliminated an entire class of weapons in 1987 relied on satellite verification. The Comprehensive Nuclear Test Ban Treaty Monitoring System combined satellite imagery with seismic sensors to detect underground tests. Even the Iran nuclear agreement, negotiated in 2015, incorporated satellite surveillance of centrifuge facilities and uranium enrichment sites, applying Katz's verification principles to contemporary proliferation challenges. The satellites themselves grew more capable. Modern imaging satellites achieve resolution measured in centimeters rather than meters. Commercial companies like Planet Labs now operate constellations providing daily coverage of the entire Earth's surface, transparency that seemed impossible when Katz was convincing skeptical Pentagon officials that overhead reconnaissance could work at all. The National Geospatial Intelligence Agency employs over 14,000 analysts processing satellite imagery for treaty verification, military intelligence, and crisis monitoring. Katz's small office at Rand Corporation in 1960 had become an entire government agency. But the core principle remained unchanged. Verifiable arms control requires objective evidence collected by technical means that neither side can evade or deceive. You can't cheat if you know you're being watched, and you won't negotiate limitations unless you're confident violations will be detected. That mutual awareness, both superpowers understanding that their strategic forces were under continuous surveillance, created the stability that allowed negotiated reductions replacing unlimited competition. The verification technology Katz pioneered continues operating today. Satellites monitor Russian strategic bomber bases, submarine construction facilities, and ICBM deployment areas, ensuring compliance with new start limits of 1,550 deployed warheads and 700 delivery vehicles. When Russia suspended participation in New START in 2023, satellite surveillance became even more critical, the only remaining verification mechanism for tracking strategic force deployments. American negotiators proposing arms control agreements with China faced the same challenge Katz confronted in 1960. Convincing political leaders that technical verification can replace on-site inspections. Katz died in 2010 at age 92, having lived to see reconnaissance satellites become so ubiquitous that Google Earth provided civilians with imagery once restricted to intelligence agencies. His 300-page classified study from 1960 proposing satellite verification was finally declassified in 2011. Revealing how completely his technical vision had been realized. The document's conclusions remained relevant 50 years later. Arms control treaties work when violations are detectable, and detection requires technology sophisticated enough to reveal what adversaries want to hide. The engineer whose camera-equipped satellites made arms treaties possible had proven that ending the arms race wasn't about trusting your enemy. It was about watching them closely enough that trust became unnecessary. Transparency, enforced by orbital reconnaissance operating at the limits of optical physics, turned out to be the foundation of strategic stability after all.